Hello everyone. Today, me and my fellow group mates are going to present to you about our final project for BMM 1223 Dynamics. Our group consists of 3 members who are me, myself, Kailashan, and my metric ID is MA22126, and Tivagaran with metric ID with MA23096, and also Madhavan with metric ID MA22111. The mechanism which is used in our project is a piston. The piston is a main component in an engine which is used to transfer force from expanding gas in the cylinder to the crankshaft via a piston rod or a connecting rod. So the system which is used by the piston is a crank mechanism. Moving on to the kinetics which is used by the piston is equation of motion, which is also known as general plane motion. And finally, the kinematics which is used by the piston is a general plane motion, which is relative motion analysis including velocity and also acceleration.
So, the example that we use to explain this system, the crank mechanism system. So, we would like to discuss about the piston, which is located in a car piston, a piston in a car. So, the value provided is the average size of a real life piston, a real life car piston. So, the dimensions are based on that. So, there are no like assumptions with small values which doesn't make sense. So before that, what is a crank mechanism? A crank is an arm attached at a right angle to a rotating shaft, rotating shaft. So which is in a circular motion. So it's imparted to or received from the shaft. So when combined with a connecting rod, it can be used to convert circular motion into reciprocating motion or vice versa. So the arm may be a bent portion of the shaft or a separate arm or disc attached to it. And attached to the end of the crank by a pivot is a rod. So this is what we call a connecting rod. So in this diagram, we would like to specify only a singular piston. So consider the following diagram on your right. Um, it's a piston of an assembly in an internal combustion engine. So the crankshaft OA is rotating at a constant rate of 1500 rotation per minute counterclockwise. If the piston is at the top dead center position where the angle is 0 degrees, the length of crankshaft OA is zero point 0.1 meter. Meanwhile, the connecting rod AB is 0.25 meter. So we can say 250 millimeter as well. The mass of link OA is 1.9 kilograms, where the link AB is 1.8 kilogram, and the mass of the piston head is 0.6 kilogram. So here we will show you three things which we calculated to give you a more detailed explanation about the crank mechanism. So this is an easy approach for you guys. So we will calculate the velocity of the piston, then we will calculate the angular velocity of the connecting rod AB and also the angular acceleration of the connecting rod AB. So angular velocity, and angular acceleration. Let's move on. So from the previous question that we read, so we know we can extract certain infos which will be helpful for our calculation. So the first is crankshaft, the angular velocity of omega OA, which is the rotation per minute. So it rotates at 1500 in counterclockwise direction. So, and the piston at the top dead center position is the angle is 0 degrees. The mass of piston head is 0.6 kilograms. Next, the connecting rod length, length of LOA is 0.1 meter, and the length of rod AB is 0.25 meter. And the rod OA, the mass of rod OA is 1.9 kilogram, and mass of slender rod AB it's 1.8 kilogram. So these details, this example, the value for this example is taken on real life example, car piston. Now we are going to look on how to calculate the velocity and also the angular velocity for the system. So first, for the angular velocity based on the rotation per minute given, so we know that the given rotation per minute is 1500. So to convert it into radians per second, we multiply it by 2 pi over 60, you'll get 157.08 radians per second. Next, the velocity of A, so which means VA equals VO, the initial velocity, plus the angular velocity of OA, link OA, times to the radius of AO, which means the length of AO. So by calculating, we can see that 0 plus 157.08 A, the vector, times 0.1 sine 0 degrees I plus cos 0 degrees J. There's negative depends on the direction. Either it's left or down, it'll be negative. If it's up and right, it'll be positive. So once we calculate it, then we will get the velocity of A, the VA, the velocity of AB is 15.708 J meter per second. Next, VB. So to calculate VB, we will get VA plus angular velocity of AB times radius of VA. So VA plus length of AB times angular velocity times sine 0j plus cos 0i. So by calculating it, we will get 15.708j plus 0.25, the length of AB, times angular velocity k, 0 plus I, and once we calculate it, we will get negative 15.708j. And by calculating to find angular velocity, the omega AB, we divide negative 15.708j divided by 0.25 I. So we will get the angular velocity of AB negative 62.83 k radians per second. So this is the velocity analysis for the crank mechanism. So you can see on my right is the free body diagram drawing of the piston in the car. So have a good look. So that's the kinematic. It's also free body and a kinematic diagram to show how it moves. Thank you.
Moving on to the calculation part of the acceleration. For the link OA is calculated with the formula of acceleration A equals to omega square OA times with R of OA. So as we substitute all the values into the formula, acceleration A equals to negative 157.08 k radius per second square times with 0.1 I meters. And the answer for acceleration A is negative 2467.3 J meter per second square. For the link of AB is calculated with the formula of acceleration B equals to acceleration A plus angular acceleration of AB times AB plus omega AB times with omega AB times AB. So as we substitute all the values into the formula, we will get negative 2467.3 I plus angular acceleration AB times with 0.25 I plus with 157.08 K times with 157.08 K times with 0.25 I, and we will get negative 2467.3 I plus with 0.25 angular acceleration AB J plus with 2467.3 I, and we will get 0 plus 0.25 angular acceleration AB J meter per second square. As we know, acceleration A equals to acceleration B. So we will get 0.25 angular acceleration AB J meter per second square equals to negative 2467.3 J meter per second square. And for the, we will get angular acceleration AB equals to 9869.2 meter per second square. Thank you.
Okay, now we're talking about calculation for momentum of inertia, IAB. So there's two, which is transitional and also rotational. Sum of forces in x-axis, that's what we're going to talk first. Fx equals to MAB times with ABX. Both values also is given. The mass of AB is 1.8, whereas for acceleration, Bx is 2467.3. So once we times both of them, we get 4441.1 Newton for x-axis. Meanwhile, for now we need to calculate for y-axis ABY, which is we already calculated 2467.3, and also we need to times with the same thing, same kg, so you will get negative this time, 4441.1 Newton, and this is for y directional. Okay, next we're going to talk about rotational equation of motion. Now we have to use the formula IAB equals to 1 over 12 times with mass AB, and also the length, So 1 over 12 times with 1.8 times with 0.25, which is the length, to the power of 2, we'll get 0.009375 kg meter per square. So from this whole calculation, we get to get about the sum of moment. The sum of moment, IAB, we times with acceleration AB. So from just now, the value, we times with acceleration AB, we get a total value of 92.60 Newton. That's all from me.
Now for the discussion, so we're going to do discussion based on the calculations and the example that we gave just now. So in the kinetic analysis, so we have examined the forces, the torques acting on the component of the crank mechanism, and also by applying Newton's second law, we established equations of motion of the system. The calculation of angular velocity and angular acceleration of the crankshaft is critical as it directly affects the piston motion and overall engine performance. We use these equations to compute the angular velocity and angular acceleration at various crank angles. So for the velocity, the piston's velocity varies sinusoidally with the crank angle reaching a maximum at mid-stroke position. So, and also for the angular velocity, the crankshaft's angular velocity is the key parameter because that's the parameter that influence the engine's power output and efficiency. And we calculated angular acceleration as well. The angular acceleration provides the insights to the dynamic force. So it's to see on the impact of wear and mechanical stress on the components. So by all this is where we can build a more efficient engine with the application of dynamics. So from the conclusion, the analysis of crank mechanism in car piston, which which comprise of kinematic and kinetic perspective. So this is important for the understanding, and also by this we can improve the engine performance and efficiency. So by calculating the velocity, angular acceleration, so we know the dynamic behavior of the system. So these calculations help in optimizing the design and operation of internal combustion engine. So we can make a better and efficient engine, we can reduce emission and increase the durability of the engine. So this study that we explain you all the way, we highlight the importance of precise mathematical modeling and analysis in mechanical engineering. So especially in the applications involving complex motion and force interaction, which we've been learning throughout the semester in dynamics. So future advancement and techniques will further enhance our ability to design and analyze such mechanism, driving innovation and improvement in automotive engineering and beyond. Thank you.